Welcome everybody from wherever you are joining the Atto Fridays today. This week, we are honored and pleased to have as a speaker Professor Nirit Dudovich. Professor Dudovich works at the forefront of laser physics and optics, and she investigates ultra-fast interactions between light and matter on an attosecond timescales. And her research links basic concepts from quantum control and applied math to attosecond science. And her group has pioneered novel schemes for attosecond metrology and applied them to review fundamental ultra-fast phenomena in nature. She earned a BSc in physics and computer science from Tel Aviv University in 1996 and received an MSci and PhD in physics from the Weizmann Institute in 1999 and 2004. And in 2004, she received the Rothschild Fellowship for Postdoctoral Studies and joined Professor Attosecond Group in Ottawa. And in 2007, she joined the Weizmann Institute of Science and established the first research group for attosecond science in Israel. So it's a big deal. And she received also several prizes and fellowships, including the 2013 Creel Prize for Excellence in Scientific Research, the IPS Prize for Young Physicists in 2012, the UPAP Young Scientist Prize in 2012 as well, and the Weizmann Award in 2021. And she received the ERC Starting Investigator Grant in 2015 and Consolidator Grant in 2019. Professor Dudovich was elected to the Young Israel Academy of Sciences and Humanities, and in 2016, she was elected to be a fellow of the American Physical Society, APS. So we're very happy to have you here today, Nirit. If you're ready to go, we are, so feel free to start. Thank you so much for joining.
Thank you very much. And I would like to start by thanking both Cornelia and Carla for inviting me to this very exciting meeting. It's a great pleasure to participate. Let me try and share my screen. So again, it's a great pleasure to participate this meeting. And in my talk, I will describe very basic schemes in attosecond interferometry, and I will show how these schemes enable us to probe in a very accurate and very sensitive manner some of the most fundamental phenomena in nature which evolve on an attosecond timescale. But before I start, let me first thank my wonderful group at the Weizmann Institute, both former and current students. And here you can see a happy picture on the beach of Tel Aviv. I would also like to thank ongoing, very fruitful collaboration we have with the Max Born Institute for many years, Bordeaux University and the Politecnico in Milano. They had a huge contribution to all aspects of our studies. One of the main challenges in attosecond science since its early days is the ability to take an experimental observable. And by the way, this is a challenge for me from an experimentalist point of view. So the question is, how do I take an experimental observable, for example, harmonic spectroscopy or photoelectron spectrum, and then trace it back into its dynamical origin? It's clear that there is some rich dynamic encoded in this observable, but how do we trace it? How do we reveal its temporal evolution? And the main challenge is, in fact, imposed by the measurement itself. Experimentally, we have a direct access to intensity-only measurement, so we can resolve the intensity of those harmonics or the intensity of those energetic photoelectrons, while the phase information is naturally lost. And therefore, if we want to take those observables, which are usually measured in the frequency domain, and trace them back into the time domain, we have to find a way to somehow restore the lost phase information. And as in many other branches in physics, phase information can be restored, can be resolved by interferometry. And indeed, interferometry has been, I think, one of the basic building blocks of attosecond science, and the demonstrations that interferometric measurement can be applied with attosecond precision led to some of the most important and exciting breakthrough in our field. And here I just gave really few examples out of a large variety of interferometric schemes. So how do we perform attosecond interferometers? Let me start with the origin of this field, or the moment at which attosecond pulses are produced in our lab. Well, here I don't think I have to introduce the very basic mechanism that leads to that generation. Let me just shortly mention it. So we can describe the generation mechanism by a very simple, almost classical three-step process in which the electron tunnel ionizes at the peak of the laser field. It is accelerated, recollides, and finally leads to the emission of optical radiation with attosecond duration. And one of the most beautiful and very useful aspects of this mechanism is the fact that we can describe it by a set of strong field trajectories which link different moment of birth, different moment within the optical cycle at which the electron can be born at, into different moment of return and different energies emitted in our spectrum. But the most important, in my opinion, and powerful aspect of this process is the fact that it preserves coherence. In this mechanism, we directly transfer the coherence of a strong laser field into the coherence of an electronic wave function that very quickly interacts with this field. And finally, all this complex information is mapped into the optical coherence of the emitted attosecond pulses. So in fact, when we resolve those intensities, those high harmonic spectrum, we realize that they contain rich information regarding the subcycle evolution of electronic wave function. And again, the question is, how do I take this spectrum, trace it back into its dynamical origin? Well, if we want to fully retrieve its coherent properties, then we have to find a way to either build or induce an interferometer. And in this talk, I will describe various different schemes for attosecond interferometry. I will show how these schemes provide us with direct access into phase information and how phase information really probe the origin of attosecond scale phenomena. And let me start with the most simple mechanism we can think of, photo-ionization. So photo-ionization is so commonly used because here we project the quantum state of matter into free electron that we can directly measure. And early in the days of attosecond science, people have used the resolution provided by attosecond experiment, raising the following interesting questions that could not have been addressed before. For example, how long does it take for an electron to photoionize? Are there any delays associated with photoionization? How will the bound wave function influence the ionization dynamics? And we can also ask, what is the role of the other electrons in this system? And indeed, over the past decade, there have been a large number of beautiful experiments providing a very direct insight into the origin and dynamics of photoionization. But since I grew up in high harmonic spectroscopy, let me go back into the very simple three-step mechanism that we are all familiar with. We understand it's an extremely accurate mechanism, since here the electron is born and must return back to the same point in order to produce photon. It preserves coherence, and it naturally provides us with attosecond precision. So the question is, can we apply this mechanism in order to probe the origin of photoionization? Naively, the answer is no, since this is a strong field mechanism which probably does not provide the proper condition to probe weak field single photon transition. But if we take a closer look, we realize that photoionization is already there. It's there at the moment at which the energetic electron approaches the parent ion and photo-recombine. In fact, we can envision photoionization and photo-recombination as the inverse mechanisms of each other. They both can be described by the same transition dipole moment. They both encode the same dynamical property. However, there is one important difference between the two, and this difference comes from an experimental point of view. In photoelectron spectroscopy, we generate free electrons and we do not have a direct access into the phase of those electrons. Instead, we can perform a measurement which is well known in our community, the rabbit measurement, which induces, by the way, an interferometer that merge together coherently two different spectral lines, and this measurement resolves the spectral phase derivative. And such derivative represents group delay, but not the phase itself. The phase associated with each spectral component in our spectrum cannot be directly resolved. But once we switch from electrons to photons, then the problem becomes much more natural, because as optician, we know how to resolve the phase of photons. So all we need is a proper interferometer. It's a simple optical problem. Well, it sounds simple. However, building interferometer that will provide us with attosecond precision is a non-trivial task that took us extremely long time to achieve. And let me schematically describe the interferometer that was built at the Weizmann Institute. It is composed of two main stages. The first one is the trivial part. We focus intense laser field into some gas cell, and we generate a train of attosecond pulses. The two fields, the IR and the XUV field, co-propagate, are reflected from a two-segment mirrors and then focused again into a completely separate gas source, generating the secondary attosecond pulse stream. And now let's look at our spectrometer. If we are able to stable our interferometer and manipulate it on an attosecond time scale, then controlling the delay between those two attosecond pulse train would lead to the following really beautiful movie where we scan the delay, and what we see is that each harmonic here beats, and it beats according to its fundamental frequency. So this is, for example, harmonic 11, and the higher we go, as you can see, the faster the oscillation becomes. So this was an experimental achievement, but it made us extremely happy because we realized that now we have a direct access into the phase of each harmonic order. And all we need is a proper reference frame to interfere with. So we started with the most simple scheme, where here in the reference source, we placed helium atoms, and the spectral phase of helium is quite flat and well predicted. And we start with a very simple experiment. Let's interfere two photo-recombination events, one from helium, the second from neon, which represents an interference between two photoionization events, helium and neon. And here is the phase that we measure as a function of energy of harmonic order. We see that this phase is rather flat, which means that the rabbit experiment cannot resolve any delays here. The derivative is 0. However, it is clearly centered around pi over 2, substantially shifted from 0, and this pi over 2 represents the phase difference between the two photoionization scattering phase, which originate from the two different ionization potential between the two atomic species. And then we can go to slightly more complex interference as between argon and neon. Here, there are quite significant group delays here. We see a derivative, and we can also identify the well-known signature of the Cooper minimum. Okay, so with Attosecond XUV interferometers, we can fully reconstruct the full coherent properties in the photoionization mechanism. In the next step, let's go into completely different ionization mechanism, and we'll take all the way from the weak field regime, where ionization is achieved by a single photon transition, into the strong field regime, where here strong laser field suppresses the Coulomb barrier and an electron can tunnel out. Field-induced tunneling is definitely one of the most basic strong field phenomena. It sets the starting point for almost all attosecond experiments I'm familiar with. And it's also one of the fastest phenomena we can think of. And indeed, over the past decades have been a large number of beautiful experiments resolving different dynamical aspects of field-induced tunneling. Let me now just focus on two questions that we would like to ask ourselves. The first one is, we know that the barrier evolved very quickly in the time domain. Can we follow the evolution of the tunneling barrier with attosecond precision? And the next question we ask is, can we probe the electronic wave function as it propagates under the tunneling barrier? So again, there have been a large number, I cited only a few, but there are furthermore looking at a large variety of different aspects of the tunneling mechanism, asking many controversial questions and providing for the first time really the proper resolution required in order to probe the tunneling dynamics. Intuitively, we understand that this entire tunneling process is an extremely short event, since at the peak of the laser field here, the barrier is strongly suppressed and tunneling probability is relatively high. Few hundredths of attosecond, the barrier lifts up and tunneling probability drops to 0. And therefore, the entire mechanism must evolve during a fraction, which can be 100, 200, 300 of attosecond, close to the peak of the optical cycle. And here is an old measurement that we have performed in our group, mapping different harmonics into their ionization time. Now, can we follow how this barrier changes with the modification of the laser field? In principle, when I look at the harmonic spectrum, I understand that the barrier evolution is already there. It's there in the intensity of the harmonics. However, we have to find an additional knob that will enable us to decouple this evolution from all other aspects of the interaction. So a simple way to do that would be to add a weak second harmonic field on top of the strong fundamental field. And this field can be orders of magnitude. It can be 2, 3, 4 orders of magnitude weaker than the strong fundamental field, such that it doesn't change the basic mechanism. It just tweaks the barrier a little bit, such that if the two fields are in phase, for example, as in this condition, then the barrier is slightly suppressed. And if the two fields are out of phase, then the barrier is slightly enhanced. So now we find in the lineup scan, the two-color delay, what we expect to see are modulations of the harmonic. Each harmonic will be modulated because we tweak the barrier, and therefore we tweak the instantaneous tunneling probability. However, and this is a crucial part in the story, when we take a careful look and we perform our analysis very carefully, we realize that each harmonic in the spectrum would oscillate slightly differently, with a slight difference in the oscillation contrast. For example, if the electron is born at the peak of the laser cycle, where the barrier is strongly suppressed, then here a tiny perturbation doesn't do much. The probability is high, so although I apply the perturbation, I will see just low contrast oscillations. However, if the electron is born later on, but when the barrier is already lifted up, then a weak perturbation can lead to dramatic modification of the barrier. So in the lab, we can look one harmonic by the other. We follow the slight modification in the oscillation contrast. And with that, we're able now to take our experiment, trace it back, and fully reconstruct what was the instantaneous value of our tunneling barrier. So let me jump to the final result. Here is a schematic description of what we measure here. We zoom into a window of about 100 of attosecond. Within this window, the barrier slightly lifts up, but this tiny change leads to a significant modification in the instantaneous tunneling probability, which drops by about 2 orders of magnitude, and we are able to see this change across the harmonic spectrum. So far, we have looked at a very simplified picture. We have considered a stationary barrier, and then we assume that somehow the barrier follows adiabatically the instantaneous value of the laser field. This is correct as long as we are in the adiabatic regime. However, in most experimental conditions, including ours, the barrier is far from being stationary. It oscillates extremely rapidly. We can parameterize this regime by the well-known Keldysh parameter. And as we all know, when the Keldysh parameter much smaller than 1, then we are safely in the adiabatic regime. However, as we approach 1, then the rapid oscillation of the barrier cannot be neglected. So the electron, as it propagates under the tunneling barrier, is in fact excited. It accumulates some initial kinetic energy, as has been observed also by previous experiments. As a result, it will be shifted to the origin when it exits the tunneling barrier, and the interaction with the oscillating barrier would lead to a substantial phase shift accumulated by the electron, and this phase shift accumulates or encodes the sub-barrier excitation. So how do we record those phase shifts? How do we separate them from all other parts in the interaction? In the previous experiment, I have shown how by adding a weak second harmonic field, we can tweak the barrier thickness, right? We can slightly suppress it, slightly increase it, and this tweaking leads to clear amplitude modulations. However, this manipulation influences not only the amplitude, but the phase as well. And let me choose one example. Let's fix our two-color delay such that the electron is born at the zero crossing of the second harmonic field. It looks like a boring configuration to choose, since at the zero crossing, the barrier is not suppressed and is not enhanced at all. Ionization probability remains the same. However, the temporal gradient of the barrier is enhanced, leading to an extra phase shift accumulated by the electron. And now when I scan the two-color delay, I can slightly increase or slightly decrease the temporal variation of the barrier, and therefore slightly increase or slightly decrease the ionization phase that the electron accumulates under the barrier. And just note, although it's a schematic picture, that the modulation in the ionization phase are shifted by a quarter of an optical cycle compared to ionization amplitude modulations. But now again, let me ask, how do we resolve this phase? It's easy to resolve the harmonics intensity. It is far more challenging to resolve their phase. And at this point, let me bring two experimental schemes together. We'll bring our ability to tweak the barrier with subcycle precision with the scheme that I've started with, XUV interferometer. Now, this is a nightmare experiment. It's a two-dimensional experiment that has to be stable with attosecond precision. And this experiment provides us with two important dimensions. Along one dimension, we tweak the barrier. Okay, we change both its gradient and its thickness. Along the other axis, we scan the XUV delay by choosing a proper reference frame, and we extract both amplitude and phase. And from one configuration of the barrier, one slice along this axis, we perform a full measurement, which provides us with phase information. And now let's change the two-color delay. We tweak the barrier. What we see along this axis, we see clear amplitude modulations, as we have seen before. But if we take a closer look, we observe phase modulations as well. In other words, as we change the barrier, the phase at which the electron is born with oscillates as well. And this phase encodes all the information we need to know regarding the interaction with the oscillating barrier. So now we have taken, this is just one example for a single harmonic 13, but we have performed this measurement, of course, for all harmonic order. And now we can now take this measurement and trace back the phase of the electron at the exit of the tunneling barrier. And here is this phase as a function of time. We see that this phase is rather flat due to the short ionization window. However, it's there, it's significantly different than zero. It's centered around pi/2. And here's just a calculation, tells us what is the prediction for the shift in the exit point. This is the adiabatic prediction. And here is the non-adiabatic correction, the shift of the exit point towards the origin due to the interaction with a barrier. So far we have looked at two ionization mechanisms, both in the weak field and the strong field, but all the experiments that we have performed were done with atomic systems, where the theory was well predicted. In the next step, let me go from atoms into molecules. And here we realize that once we go into molecules, then the problems becomes much more interesting, since here tunneling serves not only as a very accurate temporal probe, it also acts as an extremely accurate spatial probe. When the electron tunnels out through a molecular orbital, it projects the outer part of the orbital into the structure of the electronic wave function. And an interesting case to consider is, for example, tunneling through a nodal plane. And this nodal plane has to be a nodal plane in the ionized electronic wave function, followed by rapid phase variations. And now, one question that really kind of challenged me for several years is, can we retrieve those phase variation? Definitely, this phase must find its way into the harmonic phase or the harmonic signal, because it's a coherent mechanism. And if I find some nice trick to extract this phase, then I can project back and retrieve the full coherent properties of the electronic wave function, and then perhaps restore both the symmetry, the structure of molecular orbitals. Ideally, what I would like to have is the following naive schemes. I would like to take two different ionization directions and then find some clever way to interfere them together. If I can interfere them, I can resolve the relative phase. Well, unfortunately, maybe there is a way to do so, but I didn't find a direct way to apply such a scheme. But we can find a similar scheme by shaping electron trajectories. So how do we shape electron trajectories? We start with a strong fundamental field, and we add again the second harmonic field, but this time in an orthogonal direction. And with this configuration, by controlling the relative phase between the two fields, we can really shape the angle at which the electron is born and the angle of return. So it's a 2D control of electron trajectories. And we have exactly the same manipulation along the negative of cycle, just mirror image. So eventually, if we think of our experiment, again, we can describe it as a simple interferometer. This time, it's a very different interferometer because it's an internal one. It's a strong field interferometer, which is sensitive to the spatial degrees of freedom of the interaction. Each arm here is represented by the positive and negative half cycles driven electron trajectories. And if I now drive this experiment with some isotropic systems, such as gas system or randomly aligned molecules, then the experiment is really boring simply because the interferometer is balanced, so it doesn't encode any valuable information. However, once we go from isotropic system into, for example, aligned molecules, now the experiment becomes much more interesting. Let's look, for example, at the recollision. In fact, recollision can be engineered such that it is quite similar. So the angle of recollision is quite the same. However, the tunneling direction is completely different. And as you can see, along one half cycle, we can induce tunneling orthogonally to the molecular axis, and along the other axis, tunneling evolve along the molecular axis itself. So we can envision our interferometer as a two-arm interferometers which interferes together two very different tunneling events evolving orthogonally and along the molecular axis. And this experiment encodes both the relative phase, but most importantly, it enables us to extract the phase as a function of tunneling angle. So here is a schematic description of our interferometer, and in the lab we have tried that with a variety of molecules. And here I chose just one example, the CO2 molecules, and we have recorded the relative amplitude and relative phase as a function of alignment angle. So let me start with amplitude as a function of alignment angle, and we see here the well-predicted nodal plane at 0 degree associated with the HOMO orbital in CO2. But what was more exciting was the ability to reconstruct phase information and then watch the dramatic phase shift across the nodal plane due to the symmetry of the HOMO orbital. So towards the end of my talk, I would like to describe a new research direction in my group, which is, I think, also a new and exciting research direction in attosecond science, looking at extremely fast currents in condensed matter systems. Strong field light matter interaction in solid really open up a new and I think very challenging playground to look at. It initiates a variety of phenomena. Many of them are only predicted but have never been resolved so far. And one of the questions that we can ask ourselves is whether I can take all these very simple interferometric tools that have been developed for the gas phase system and apply them now to solids such that we have a direct access and a very accurate one into these phenomena. When the field strength approaches several volt per angstrom, it becomes comparable to the band gap energy of a one lattice site. So in this regime, the band structure itself can be dramatically modified, changing quite significantly the basic properties of the medium. So I think the most exciting observations in our field were the realization that indeed some cycle changes in the conduction or the absorption can be induced in a reversible manner during less than one optical cycle. And one of the most important, I think, discovery was the understanding that harmonics can be directly produced from a solid state target. The basic mechanism that describes harmonic generation in solid has been, I think, later explained by various mechanisms. Let me just focus on one mechanism that was first described by Julia Vampa and Paul Kokum in Ottawa NRC. And this mechanism is closely similar to the one that we are familiar with in the gas phase case. At the peak of the laser field, an electron can tunnel from the valence into the conduction band, initiating an electron-hole wave packet. And this wave packet quickly propagates within the band structure. It can reach all the way up to the edges of the beryllium zone. It can excite higher conduction band until at a certain point in real space, we have an overlap between electron and hole leading to the emission of attosecond pulses or harmonic spectrum. Now, this electronic wave packet is very well localized in K-space, and therefore we can think of it as an extremely accurate probe of the band structure itself. So we ask ourselves, can we use harmonic spectroscopy in order to probe the shape of the conduction band and perhaps of higher conduction bands in the system? And can we take one step further and perhaps watch how this band structure is modified as it interacts with a strong laser field? So in order to study harmonics in solid, we have started with the most simple system to consider that has extensively studied by many groups and pioneered by the group of David Rees in Stanford. We'll look at harmonics from magnesium oxide. And here is a typical spectrum that we observe at 0 degree. Very similar to David Rees, we see the appearance of sharp peaks in our spectrum, which are very different compared to the gas phase case. And we were also extremely happy to see the appearance of higher order harmonics, which go far beyond the cutoff imposed by the first conduction band, which means that we have here harmonic emission for several higher conduction bands. And then as we rotate the crystal, the spectrum changes quite dramatically, leading to the appearance of new sharp spectral features. And for quite a long time, we were puzzled by the question, what is the origin of those sharp spectral features? What is the information that they encode? And let me start by looking at the band structure of magnesium oxide. This is the valence band. This is the first conduction band, and several higher conduction bands. And now if I simply and very naively try to link those sharp spectral features with a point in the band structure that leads to their emission, then there is no clear conclusion we can make here. However, if instead of looking at the band structure, let's look at the band gap, which really dictates each harmonic order, dictates the photo-recombination event. Okay, and this is simply the difference between conduction and valence. Here, we observe a striking conclusion that each bright spectral feature is associated with a critical point within the band gap, with a point where the gradient of the band gap approaches 0. So what is so special about those points? Why do they lead to sharp spectral enhancement? If we think of our very simple semi-classical picture, then this picture maps different trajectories in K-space into frequencies in our harmonic spectrum. And along the Brillouin zone, we have a one-to-one mapping between K and energy. However, at a critical point, we have not a single trajectory, but an infinite number of trajectories, which all coalesce together, they merge together constructively and build a huge constructive interference. Here, there is a singularity in the mapping between K-space and energy. And as in many other phenomena in nature, whenever we have singularity in the mapping, it may lead to the appearance of caustics. And these are caustics which are very similar by nature to the caustics that you would observe on the surface of your swimming pool or at the top of your coffee cup. By the way, the same caustics appear at the cutoff energy in gas phase high harmonics and in many other attosecond phenomena as well. So here we understand that the band structure really dictates the brightest feature in our spectrum. So let's take one step further and ask whether this band structure can now, or alternatively, can we identify field-induced band structure? If we increase our laser field, can we see how the band structure is being modified? And probably the best place to look in our spectrum is the most sensitive one, where harmonics are emitted within the band gap. So this is the first and the second conduction band in magnesium oxide. And in our lasering condition, looking slightly above harmonic 19, between 19 and 17, we have the band gap between those two bands. And we understand that any tiny modification of this gap can lead to dramatic enhancement or suppression of these harmonics. But again, let me raise the question that we have raised in the gas phase. How do we decouple band gap modification from all other parameters in this measurement? And of course, as we go to condensed matter system, the interaction itself becomes much more complex, and there are additional parameters that influence our harmonic spectrum. Ideally, I would like to have some ideal experimental setup that will provide me with a knob, an external knob, that will allow us to slightly close or open this gap. Unfortunately, I don't have such a knob, but what we can do is simply rotate the crystal, okay? And if these are the two conduction bands, at 0 degrees, a rotation by about 20 degrees completely closes the gap. And then they are really merged. So by slightly tilting the crystal, we induce a quite dramatic transition between two completely different dynamical regimes. In one regime, the harmonic is emitted from the gap. In a different, and now when we rotate the crystal, the second regime is harmonic emission from the band. Okay, it looks quite dramatically and it must map to our harmonic signal, but the question is, how do we resolve such transition? Let's bring our favorite tool, and this will be the second harmonic that we have used before In the previous case, in the gas phase case, we applied a weak perturbation of the second harmonic to tweak the tunneling barrier. In this case, we apply a weak perturbation of the second harmonic and we can tweak the gap. We can slightly close or open the gap and look for the modification of the signal. And of course, as we scan the two-color delay, then the harmonic that we're looking at will oscillate. In fact, all harmonics eventually oscillate, but the oscillation phase is a very sensitive experimental observable which encodes valuable information about the interaction. And now let's extract this phase, and this is what we have done in this experiment, and watch how this phase changes when we rotate the crystal, how this phase changes as we go from gap emission to band emission. So we have focused on the phase of harmonic 20, which lies really within the center of the gap. And here is the oscillation phase at 0 degree. And now we rotate the crystal, and after 15 degree, we see a dramatic jump by about pi radian. And then the phase, by the way, the absolute phase is kind of random. What we should look at is the angular variation of this phase. And then the phase remains flat. Okay, we rotate the crystal, but nothing really changes. So we already understand that we are probably sensitive to a transition between the two dynamical regimes, gap emission, band emission. And now we are ready to increase our laser intensity and watch how this transition is modified. We increase the laser intensity and we see that the jump becomes smaller and smaller and smaller until it becomes really difficult to distinguish between the two dynamical regimes. In other words, there is one regime which dominates them all. In a careful theoretical calculation performed by the Max Born Institute have concluded that this experiment reveals laser-induced closing of the band gap between the two conduction bands. And since the band gap is closed by the laser field, then there is no transition between the two dynamical regimes, and the entire interaction is dominated by band emission only. So with that, I would like to thank you for your attention. Let me just summarize. Attosecond interferometry enable us to reveal more and more fine details regarding fundamental quantum phenomena in nature. And while attosecond science has been extremely successful looking at the variety of phenomena in gas phase system, my personal challenge would be now to go into condensed matter. I think we are just doing our first steps in this direction. And here, I hope that developing new interferometric technique will enable us to probe more complex dynamics, all the way from band structure to multi-electron. For example, can I apply interferometry to watch multi-electron phenomena or even subcycle phase transition? Thank you very much.
Thank you so much for this really nice talk. Are there questions, comments? Do feel free either to raise your hand or to put your comment or question in our Q&A tab. Before we start, I would like to make a few announcements. The first one is that for 2022, we are planning to organize sections for early career researchers, which we are going to call hot topic sessions. You can apply until the end of the year. I have just put in the chat a link to the hot topics. So basically, the idea is if you would like to talk about something hot that you have done and interesting, and you are an early career researcher, either PhD student or postdoc, send an email to quantumbattles@gmail.com, which is our official email, and let us know why you should talk and send an abstract. And we're going to select these talks in January. So they're going to be 2 25 plus 5 minute talks. If you also are a PI and you know of a good PhD student or postdoc who would like to talk, do send us an email as well. we think, especially in these times, it's very important to support early career people, because due to the pandemic, they have missed a lot on socializing, on meeting people, on speaking. And this is a way we would like to use to facilitate that. And the other announcement is that our special issue in European Physical Journal D, Quantum Aspects of Attoscience, is still accepting contributions. In fact, the deadline has been extended due to the pandemic up to the 31st of January 2022. If you would like to contribute, do send us something. We accept as well tutorials and review articles. So do have a look. And again, we would be happy if you would like to contribute. There have been some contributions associated with this series and also with the 2020 Quantum Battles in Attoscience that we had also online. So these are good opportunities. Okay, I'm biased because we're organizing it, but still, don't miss. And I'm looking forward to your questions. Is there any question, any comment anybody would like to make?
I mean, while our audience maybe is still processing for a bit, I can try to see if I can formulate the question, because Nirit, you really piqued my interest when you started talking about non-adiabatic effects in the section where you looked at probing the wave function under the barrier and how that not only has an influence obviously on the energy and its exit position, but also on the phase of the electron. So I was wondering if you could expand a little bit more on that.
So one maybe simple way to think of this phase, when I'm trying to get some intuitive picture of this phase, well, we can also associate that with some additional delays, which add up to all other delays that we're familiar with. So one kind of basic way to think of it is that when an electron interacts with some oscillating field, of course, it acquires a phase. And if we're in the adiabatic regime, this phase would be zero, but the oscillations of the barrier are somehow there in the along the stationary path of the electron. But if you take the derivative of this phase, you would get some tiny extra delay that the electron accumulates. And when we try to think what is the intuitive explanation behind this delay, then we think that we can explain it as somehow link into the tiny shift in the exit point. So if you shift the electron to be closer to the origin, then it will take him slightly longer time to reach the same point at which the adiabatic mechanism predicts. And so that can be linked. And if you integrate that over frequency, then you will get the phase. But
okay,
just an intuitive way to think of this phase shift.
Yeah, makes sense. Thank you.
So any more questions, comments? Would anybody like to ask anything? Okay, so I will start then. In your opinion, what are the biggest challenges when you're looking at solids in strong fields? Because from what I understand, there is much more flexibility than with gases, but there are challenges too.
This is correct. Of course, there are many experimental challenges that we didn't face in the atomic case, as the damage threshold and propagation, phase matching, the absorption of the XUV, but these are experimental challenges. I think from the point of view of attosecond spectroscopy, when I entered this field, I really love the elegant picture where no matter how complicated the system was, we can always somehow decouple the complex system, which includes tunneling and everything, from the propagation in the continuum. But in solid, this cannot be done. So the problem is that I cannot easily break the interaction into its part, and everything plays a role. So harmonic spectroscopy was so successful because you could think of this trajectory as kind of a probe that you accurately manipulate. But now your probe is influenced by the system as well. If I rotate the crystal, I manipulate this trajectory as well. And I think one of the most difficult challenges is how do we decouple the different degrees of freedom? How do we isolate what we want to look at? And this is something that really puzzles me. It's not clear how this can be done.
Yeah, thank you. Thank you so much. We have a question from Mona Lisa Malik. It was a great talk. I am new to this field. So the laser which you use is all CP stabilized systems only?
In fact, no. None of my laser systems is CP stabilized system. The reason why it works is that, in fact, we work in the infinite field regime. You can think of the attosecond event as repeating itself exactly under the same conditions at different optical cycles, and then all the contribution interfere in the high harmonic. But what provides us really with the attosecond resolution, the fact that the two fields, the fundamental and the second harmonic, are locked in their phase. So I don't have to lock the absolute carrier phase. All I need to do is to lock the fundamental with respect to the second harmonic, which is, by the way, an easier task. I hope that was clear.
Is that okay? Would you like to ask further? If so, let us know. So you're allowed to talk in case you would like to ask. It's absolutely fine if you're new to the field. We have all been new to the field at some point in our lives, some sooner, some later. So if anybody else is new to the field, her microphone is not good. Okay, fair enough. And she's good with the answer. So thank you so much. So for those who are watching us on YouTube, thank you so much for supporting our initiative, and hope to see you soon again in the Atto Fridays. And thank you also to Professor Nirit Dudovich for her really great talk. So bye, see you soon.
Thank you.